This is presentation of a poster that was intended for EB2020 that was supposed to be held in April of this year in San Diego. The project is on rational design, synthesis, and in vitro evaluation of smart, uncharged bis-oxime antidotes of organophosphate-inhibited human acetylcholinesterase. This is a collaborative project between several different institutions, primarily University of California at San Diego, Oak Ridge National Laboratory, Ohio State University, University of Utah, and our first author is visiting graduate student from University of Hradec Králové in Czech Republic, now Dr. Lukas Gorecki. My name is Zoran Radić, and I'll be talking about details of the project. So this is about human acetylcholinesterase, key enzyme in cholinergic neurotransmission. Its primary physiological role is hydrolysis of neurotransmitter acetylcholine. Here you see a Connolly surface of one catalytic subunit of human acetylcholinesterase and small molecule of neurotransmitter right above it. Neurotransmitter has to traverse about 20 angstrom deep and narrow path to get to site of catalysis in this enzyme. And looking now from above, at the base of that active center gorge is located active serine. This active serine is target of organophosphorus compounds, either nerve agents like VX, serine, cycloserine, or organophosphate-based pesticides. Parathion is one example, and paraoxone is its active form. Once they approach active serine, they covalently bind to it and they form inactive, catalytically inactive enzyme. Our goal is to attack this inactivated enzyme by small nucleophilic antidotes and recover its activity by breaking a phosphorus-oxygen bond between organophosphate and active serine. Typically, antidotes that are in use for this type of reactivation are pyridinium derivatives. 2-PAM or pralidoxime is one of approved antidotes for this type of therapy. MMB4 is experimental antidote. A common property of both of them is that they are positively charged, and while they reactivate enzyme in test tube really well and enzyme in peripheral nervous system of our body also really well, they cannot access central nervous system, an enzyme that is inhibited in central nervous system. Therefore, we need antidotes that are not positively charged, and one example is RS-194B, antidote developed in laboratory of Palmer Taylor at UCSD. That was our lead in design of new antidotes that can traverse blood-brain barrier and reactivate enzyme in brain. In that project, we were guided by several crystal structures. One of them was MMB4, charged antidote in complex with VX inhibited enzymes, sold by Oksana Gerlits. And here you can tell nucleophilic oxygen of MMB4 approaching phosphorus really nicely. However, when Oksana solved X-ray structure of RS-194B in complex with VX inhibited enzyme, the nucleophilic oxygen of the oxime group was pointing in completely opposite direction away from the VX. So even though this antidote is effective both in vitro and in vivo, X-ray structure is showing that its dominant binding orientation in the enzyme is not correct. Therefore, and these are some details of its binding in active center gorge of VX inhibited or native enzyme in both complexes. It is pointing towards opening of the active center, so in the wrong direction. Therefore, we started, and that was work led by Dr. Xiaolin Cheng of Ohio State University and his group, but also in collaboration with Andrey and Oksana. They designed several hypothetical computational compounds, and we all worked on that. And then came Lukas from Czech Republic, and at the School of Pharmacy, under guidance of Carlo Ballatore, synthesized 7 of those compounds and performed initial physicochemical characterization. When we solved X-ray structure of one of them, it showed really nicely correct orientation of nucleophile pointing towards site of organophosphate reaction. An enzyme and a group of undergraduate students at UCSD, Stephanie, Yunshen, Celine, and Bianca, helped us characterize reactivation properties of this group of new antidotes against the VX inhibited enzymes, serine inhibited enzymes, cycloserine, and paroxone. I have to say that in these experiments, students did not work with any of those very toxic compounds. We generated organophosphate inhibited enzymes using analogs that are very low toxicity because they are not volatile, not hazardous. So in any case, structure of inhibited enzyme is identical to structure of enzyme inhibited by actual nerve agents. Not only that they performed initial characterization, they did a little more of kinetic work in reactivation, but this initial data show that compounds were more reactive, better nucleophiles that are lead. Lead is shown by green bars and gray bars, and orange are new compounds. The higher bars mean better reactivation, so we got better reactivators in vitro. They evaluated several reactivation constants for each combination of antidote and inhibited enzyme. Maximal rate of reactivation, the first order rate constant K2, Michaelis-Menten type constant Kox, and overall second order reactivation constant Kr. When we let's look at Kr, this column shows a set of numbers. The larger number means better reactivity, and when we look at RS-194B numbers, they are typically lower than numbers above of our new compounds, so that means they're in test tube, they work really well. There is one interesting and important feature of these new compounds, and LG703 is here shown as example, and that is that because they have 4 ionizable groups, they can be protonated, but they also equilibrate between anionic and uncharged forms. In fact, one of each of these compounds with 4 ionizable groups can equilibrate between 16 different ionization forms, and 2 of them are of particular interest for us. One is uncharged form, and here is distribution of uncharged species for all 7 compounds in comparison with our lead RS-194B. And at physiological pH, this was calculated from Lukas's initial physicochemical characterization of each compound. He did it by potentiometric titration. So those numbers show us that each of those new compounds can form a significantly larger fraction of uncharged species than a lead compound. That is important because only uncharged forms will spontaneously diffuse through biological membranes, including the blood-brain barrier. For reactivity, nucleophilic reactivity, we need a zwitterionic form, and these compounds have several, more than one zwitterionic form, and typically fraction at physiological pH of those was higher than a fraction that we determined for our lead RS-194B. So all of that, those are very promising data, and currently we are proceeding with some in vivo experiments of initial toxicity and pharmacokinetics to show that indeed these compounds can access brain and that they are not very toxic. So we know now that they're indeed of low toxicity, but pharmacokinetics is ongoing. At the molecular level, it's really important that while on the paper, some of these compounds, or most of them, are symmetric, like LG703, in fact, X-ray structures show that they are not symmetric, and that is due to the fact that the central cyclic ring where cyclic amines are located, both cyclic amines are not protonated, only 1/2. This is important for us because here, for example, you can see 3 different arms, each bearing nucleophilic oxime group, 2 in LG703, the third one in RS-194B. They're all structurally the same, but their conformation is obviously different. In fact, from several crystal structures that Oksana saw so far, we have observed several discrete sets of conformations of this side chain depending on ionization state. For example, here, RS-194B is always protonated at physiological pH here, the only cyclic amine that it has, but the oxime group is either protonated or not protonated. And depending on that ionization state, conformation of the oxime-bearing arm will be different. So we see several different conformations. That means that single compound, like LG703, can assume several different conformations of attacking arm while attached to the same location, to the same point in the enzyme. And that is one important feature of this set of compounds, in that their geometry is flexible. It's not continuously flexible, but there are discrete conformations that those compounds can adopt in the active center of enzyme. For more details, see our article that's recently published in JBC. And now let me show you some molecules in virtual reality. So here is the poster. Lukas is standing right next to the poster. We were looking at these slides here, and this is our molecule of acetylcholinesterase. And as you noticed before, I was showing how narrow and deep active center gorge is of enzyme. This is acetylcholine based on X-ray structure, several X-ray structures that were solved before, of complex substrate with enzyme. The predicted way it acts it slides down the active center gorge. What one can notice is that this is very tight fit, and what you're seeing now is slow descent. The actual rate of descent is several fold faster, and right now you're seeing 2 molecules per second accessing active center of enzyme. In reality, enzyme under optimal conditions works 5,000 times faster. So imagine this times 5,000. That is how many molecules of neurotransmitter can single molecule of enzyme hydrolyze hydrolysis. And the main feature of this hydrolysis is that it happens in very narrow active center Gorecki. Now let's look at inhibited enzyme. This is our VX inhibited enzyme, and this is structure that I showed with antidote that was pointing in the opposite direction. It is very easy to see here that the direction of nucleophile is opposite from the site of covalent bonding of phosphorus that is exactly here at the active center of enzyme. So when we create our antidotes, we need a nucleophile that will point towards that phosphorus. So this is the way it should point. It should point somewhere inside, and overlay of different conformations that I've shown before is in fact this. These are possible orientations of nucleophilic attacking groups versus phosphorus that they have to attack. So we have here a set of nucleophiles that are all attached to a single point in the enzyme. There is particular tryptophan that will stabilize protonated cyclic amine here very nicely, but then flexibility of this arm will allow, limited flexibility will allow for different geometries of attack, and that is something that we have not seen with antidotes before. Let me clarify this a little bit by undisplaying our non-productive antidotes. So here you see only productive orientations and how anchoring of antidote at one position can result in several different geometries of attack. This is of particular importance because each organophosphate and pesticide is structurally different, and after conjugation, covalent bonding to enzyme, it will form a different structure of the target. So flexibility of the antidote and its ability to cross blood-brain barrier is of critical importance. Thank you very much.